Good morning, Şükrü Hocam.
Good morning. Good morning. How are you today?
I'm fine, and you?
I'm fine, thank you.
Oh, today the first presentation is your
Yes,
presentation, right?
it's my presentation.
But I think there's a problem with the video file.
That's okay. I'll do it live.
Okay.
So that's better.
Okay.
So I realize there is a problem with the file because you cannot read the text.
Yes.
So I want to make it smaller, but didn't work out. So I'll do it live.
Yeah.
Should I start or sorry?
The page couldn't see clearly in the video file. Yeah.
Yes, that's true. That's true.
Yeah. If you are ready, we may start with your presentation. Okay. First, I introduce myself. Okay. My name is Hakan Gürün. I'm from GAZİ University, Department of Manufacturing Engineering. My specialty is deformation technologies, especially the sheet metal deformation techniques. And I am the session chair of this session. As you know, the presentations will be recorded by Zoom and shared in YouTube. And if you are ready, we may start with your presentation. You can share your screen. Yeah.
Okay. I'll share my screen first. Okay. Just a minute. Right. Okay. So I'm ready. Shall we start?
Yep.
Okay. So my presentation is about the application of ESD coating on die surfaces or mold surfaces. This is a case study with a large die that is used for sheet metal forming. This study was carried out in Yıldız Kalıp, and it's a company in Istanbul. And at that time, I was also helping them with the findings. This is my outline. I'll present the case with short introduction. Then I'll give you a short literature as well. And I'll mention about materials and methods, results and discussion, and finally, conclusion. So what is the aim of this study? This is very important. Most die steels are DIN 1.2379 tool steel. They are very durable, high wear resistant, and it's a little bit expensive, but because of their high wear resistance and hardenability, these steels are preferred over low-cost steels. But what we wanted to do is that in a die, there are regions that you're not using fully. So the disadvantage of cheap steels or less alloyed steel is that the hardness is not that high, but it's not a big problem. The problem is stretching or wearing is also a big problem, especially some parts of dies. They are very susceptible to wear, especially where the sheet metal is running on the die, corners or small angle parts. These are very important design problems which you cannot overcome. So we have decided that, okay, why don't we use IC 1045 or CK 45 steel in place of 2379, and let's define the problems in this die. For example, so where is the most susceptible area to wear? So if we can determine these areas and coat them with very hard surface materials or hard facing, then we can overcome the problem, because rest of the die is not that susceptible to wear. So the study started with a special die, or we have determined this is very important die, so let's work on this. And we have determined the high wear areas. Then we coated them with tungsten carbide and stainless steel plus tungsten carbide with ESD method. So the aim was to make it cheaper, and in this way, so die steels or more expensive ones are used less. So that was the aim of this study. So what is ESD process? ESD process is called low energy welding or low energy arc welding. You have an electrode. With that electrode, it's continuously rotating. When it touches the surface, because there is an arc flow or electric flow, it's as soon as it touches the surface, it will create a small amount of molten area. It's a melting pool, arc pool, and with this arc pool, you will alloy the surface with the electrode. As soon as you're done with this process, that area solidifies and newly formed or newly alloyed surface is created. You may use tungsten carbide. As long as the electrode is conductive, you may use different type of materials to coat the surface. You can coat the surface of steel with 2379, tungsten carbide, titanium carbide, plus titanium diboride. So you can have very hard surface, hard facing, actually, a very hard surface hardness by the alloying of the surface. So we have two parameters in this one. The first one is frequency, how often you create arc, and the current. With the current, you can determine the thickness of the layer. With the frequency, the amount of deposition on the surface. It's a very flexible process. It doesn't have to be automated. You can do it manually. Because it can be done manually, the process is very versatile. So you can use it on the tank, you can use it inside the tank, in closed area, open area, etc. As long as you have a protective environment for metals like aluminum and titanium, etc., there is no problem. For steel, you don't need protection. So let's talk about small, this coating of the surface, this IC 1045 steels with ESD coating. The ESD coating on these steels are done extensively. So as far as literature goes, it can increase the surface hardness at least 5, maximum 8 times. So you can have 10,000, 1,000 Vickers, or a little bit over than 1,000 Vickers if you have enough thickness of the layer. And what they realized, it's this hard surfacing reduces adhesion wear on IC 1045. But this is a general rule for hard surfacing. Because they are very hard, they don't attach the surface very easily because it doesn't get softened. Another thing is the friction coefficient of these coatings are very low. It can go down as low as 0.18 with tungsten carbide coating, and wear mechanism changes dramatically, mostly from adhesive wear to we call it fatigue wear. But fatigue wear happens because it's a layer. If it wasn't a layer, if it was, let's say, heat treated afterwards, that would be different wear types. Is there anything else? Yeah, we can coat the surfaces with tungsten carbide, titanium carbide, tungsten, as long as the electrode is conductive, as I mentioned before. The surface can be coated very easily with any ceramic material. It can be coated with mixture of compounds, like you can have titanium carbide plus titanium diboride, or titanium carbide plus tungsten carbide at the same time. This is also possible as long as you have an electrode. The coating, as I said before, we have two parameters. Although it says volt here and power, power is more important than the voltage. Power is directly related to current, the amount of electron you deposit, you transfer from one electrode to another. So another parameter was frequency. So in this case, we have used 300 hertz. Well, it can go up to 1500 hertz, 1.5 kilohertz. Afterward, it doesn't mean anything. You can go down to very low frequency as well, like 100 hertz. But what we found on this research is that 300 hertz is enough for us. So we use 60% power and 300 hertz. 60% power is approximately 25, 26 amps. And it would be enough for us because we don't want to create a very hot surface. Another advantage of this process is that when you're welding the surface, the heat generated is not high enough to create metallurgically different substrate, and it doesn't affect the metallurgy or microstructure of the substrate as well. So it's very important. So we coated the surface, as you can see on the picture. This what we did with the whole die, we didn't use the whole die. What we did is we cut small piece from the middle, we coated that part, then put it back and screwed. On that small part, we did 2 layers. I'll show you later. We did 2 different zones, and in both zones, we could use the same parameters, sheet metal parameters. In this process, because it's titanium carbide and stainless steel, we used argon purging. We coated area, we covered the area with argon. Then EST coating was done. What we did is that we tested sheet metals after 50 and 500 pressings. So we took out the sheet after 50 pressing, then 500 pressings. So we compared those two. You will see the difference. It's very obvious. Anyway, these are the steels. As you can see, the CK45 is $800 per ton and metric ton, and the steel that we replaced, 1.2379, is $3,500 per ton. So we are making very good use of this process if it works, and it's very expensive as well. In this, it says $3.50, but when you're cutting and selling them separately, it becomes $6, $7 per kilogram. So it's very expensive. So what we did, we did metallurgical analysis on the specimens using optical microscope and electron microscope. We also measured the hardness of the surface. This is the steel or general view of the die. it's not steel, it's die. And so it's actually two parts, but we applied to this, there's a small insert here. Okay, sorry, you can see it in B. There's a small insert here. In this insert, it can be taken out. You can replace this with another. If it goes bad or if it's worn, you can replace it. So what we did tungsten carbide and stainless steel and tungsten carbide separately. So we made sure that these corners are different materials. So the forces on these corners are equal, so it's same. So we use this part for tungsten carbide and stainless steel and tungsten carbide. Only tungsten carbide on this part. So we have, instead of coating everywhere, we just coated that insert. That was the important part, because the rest is not used much. So it's important that this is a manual process. Because it's a manual process, it's labor intensive, which means somebody has to sit and do this coating very efficiently. So instead of coating places where there is no wear, there's no point doing those coating those places. So we coated important parts. So this is the result. When there is no coating on the surface, you can see stretch marks and scratches on the surface. This is, if you're doing sheet metal forming, this is quite normal, but these scratches are because of the asperities on the die surface. Die surface is not holding up. This is what we call. Because it's holding up, it's although it is hardened after 50 sheet metal processing, the surface is coated with metal from the sheet or pieces. Those pieces are causing adhesive wear on the sheet metal and also the die mold surface. So those stretch marks are created because of the die. If the die surface is not clear, or it has some asperities, it has some defects, these problems occur. The problem is that these can be resulted in rejection of parts. So a company might say, okay, this is too much, I'm sending this, send me another parts which is better. 500 sheet metal pressed after coating, you see there is only very small scratch here, and the rest is very clear. It's extremely clear, and we were not expecting this. We were expecting maybe 100 or 150. We kept looking at it, and nothing happened. We were shocked. So it's a very good surface quality, and the company was also very happy with this result, because they could save thousands of dollars on die metal and sheet metal. With the sheet metal, they are sending, the quality is good. So the receiving company obviously is very happy that there is no stretch marks or wear marks. And they also very happy that the receiving company congratulated them that your sheet metal processing is very good. And but there's a slight problem with this, that it's a disadvantage. Somebody has to sit and do this manually, so that's the only problem. So now they are working on automation of this processing and see what they will do. So we did some optical work on the surface. As you can see, these are this one is tungsten carbide coated. This one is tungsten carbide plus stainless steel coated surface. So the base hardness was around 189 VCARs or 189, 200 VCARs. So tungsten carbide plus stainless steel coating created 290 HV extra. So you can add 490 VCARs. This one is 610 VCARs, became 610 VCARs. So the hardness increased quite a lot. But the problem with these coatings is that what we do coat the surface with stainless steel first, then tungsten carbide to make sure that tungsten carbide layer is not cracked. But because there are two different alloying zones, these alloying zones creates different softness. So if tungsten carbide steel interlayer is not as soft as stainless steel and substrate interlayer. So stainless steel substrate creating a soft zone with austenitic steel 316. So we think that because of the softness, you can see horizontal defects on the surface. As you can see, horizontal defects, the amount of horizontal defects are higher than the amount of horizontal defects in tungsten carbide coated surface. So this surface harder, it's not easy to deform, but because of these repeated processes, these defects are forming, and it's easier to form on stainless steel coated surface because it's soft. And as I explained, there are two different zones here. The first zone is stainless steel CK45 zone, and another zone is that when we are coating tungsten carbide, another alloying zone is between stainless steel and tungsten carbide. So we have two different alloying zones. The first alloying zone is very soft. Because of this softness, the surface, the tungsten carbide cracks happens on the surface, and this because of the friction, this interlayer, soft layer, moves along with the sheet metal. It's still doing the job, obviously, it's still doing the job, but after a while, this surface was worn faster than this one. So just coating tungsten carbide of the surface, die surface, was better than coating stainless steel and tungsten carbide. So these are the results of die surface defects. This is tungsten carbide plus stainless steel. As you may see, it's uneven edges, and also there's a depth to it, which means it is an adhesive wear. So what happens when you're moving the sheet metal takes some part from the surface and takes that small part with it. But in the first one, tungsten carbide, because the underneath is very flat, very smooth surface, we think that this layer, tungsten carbide layer, worn because of repetitive deformation, which means fatigue deformation. This is the fatigue wear, and this seems to be the adhesive wear. So the alloying, in fact, is very good, no problem with alloying, but it changes defect formation, a type of defects in both coated steels. Not sure which one is the best, but what we can do, if the surface is worn, we can clear the surface and do the ESD again. So that's the advantage. So with hardening, as soon as that place is, that worn place is appears, that worn place is obvious, then you have to weld it or hard surface it, then grind it. But in this method, you don't have to grind as well. You can do ESD coating on top of this coating layer. So there's an advantage to this method. So hardness increases. and scratches almost gone, and the surface hard, because the surface hardness is high, the wear type also changes. The difference between these two is the alloying, or two different layers. One is softer at the bottom, and the other one is hard. So that's another advantage and disadvantage. So company applied, now they are coating their dies with tungsten carbide electrode. Important, but not everywhere, just where the wear is happening, and this is giving them big advantage as well. Even if the substrate is 2379, you can still do this coating and tungsten carbide coating, and they successfully applied these coatings. So in this study, we can conclude that, by looking at 50 and 500 pressings, we can say that the ESD coating of tungsten carbide and coating with tungsten carbide and tungsten carbide stainless steel of CK45 steel was successful. So they were it was successfully applied, and they were very happy that they could save some money, because these industries are labor intensive, and they have to spend so much money on CNC processing, heat treatment, and profit margins are not large. If they are selling the die outside of Turkey, if they are exporting it, they can earn some money. But within our country, there are so many companies doing this die forming, so profit margins are not high. So they are trying to save on steel as well. The observation of horizontal scratches suggests us that tungsten carbide is better than tungsten carbide plus stainless steel, and because it increases the surface of the steel, especially specifically designed areas, we can get an advantage of wear rate, especially with tungsten carbide compared to tungsten carbide plus stainless steel. Another advantage is that very big advantage for fabricators or producers is that the service life is extended. Because the service life is extended, they can press more sheet metals, and time is money, so they can earn more money. This is the outcome of this study. This study was done in 2007, started in 2017 and ended in 2018, and it was supported by TÜBİTAK. Thank you very much. If there's any questions, I'll be very happy to answer.
Thank you for this good presentation, and I think there is no any other questions, but I have a question. Maybe you said that, but I didn't catch it. You mentioned that there are some important areas in the die where wearing occurs, yeah, right?
Yes.
I didn't catch it. How did you define the wearing areas in the die? Because it's related to the parts, right? And so it will be changed from part by part. Did you apply it to the used dies?
Yes, that's a good question. What we did, they produced this die, and after producing this die, they used it for 100 pressings. Then they checked where their wearing is happening. So what we did, we ground that area and coated with tungsten carbide. With tungsten carbide plus stainless steel. Our chance or our advantage was there were two regions with the similar wearing capacity. So we could use tungsten carbide and tungsten carbide plus stainless steel. It's also possible to find out where high wearing is possible with simulations. They did simulation first on some simulation program. I don't know which one. I think it was Deform. And there were some red areas, which means higher straining areas. With high straining areas, we defined it first, then we applied. I mean, as I say we, but I didn't do the job. They did the job. Then we said, okay, let's coat these areas, see what happens. They were not expecting that much. You know, it would fall off because the coating they did before was not. They were not happy with the coating. They were spalling. There were some spalling problems. There were some cracking problems. They did thermal sprays. It didn't work out because it's high straining areas, high worn areas. There are great forces that apply to this on this sheet metal because the surface is large, and also they are using GP 800, which means this as the strength increases, the force that you're supposed to apply to make the shape change is higher. So dies wear faster if you're using high strength steels. This is the big disadvantage. So we could first model it, then use it, and find out where the wearing is happening. Then we apply these coating accordingly.
Okay, thank you. I think your study is very important for reducing the die cost, right?
Yes.
It's very important for die manufacturers and sheet metal parts manufacturers. Yeah.
And automotive spare parts manufacturing companies, they can benefit from this a lot. I mean, after this project, they used to have so many dies they were lying about, and they have decided to coat them with this method, and they were happy that, you know, you said you're using it 24 hours a day, so
sure.
I'm glad they made use of it.
Yeah.
That's what I'm saying. Thank you very much.
Thank you so much.
You're welcome. Thank you,
Dr. Talas. Thank you so much. And now let's continue with the second presentation. The second presentation is calculation of change in soil density under twin valves of a tractor. Dr. Alexander Solarov will perform this presentation, but I think he is not here, but he sent us a video file. Now I will run the video file if I can do it. I'm not really good at this kind of things, but I will try my best.
your best. Your best.
Conference organizers, dear colleagues, my name is Solarov Alexander, PhD, Associate Professor, Sumy National Agrarian University Faculty of Engineering and Technology, Sumy, Ukraine. And today, topic of my presentation, calculation of changes in the soil density under twin wheel of a tractor. One of the most common change in agriculture today is soil over-compaction with the wheels of tractor and other machines. This is due to an increase in the weight and number of machine operation in the field. Many agricultural enterprises neglect this fact. This in turn leads to a decrease in crop yields. Therefore, in my opinion, this issue is one of the matter of current interest. In this slide, we can see how the field look like in case of improperly selected tillage technology and soil our compaction with the wheels of operating machine. The first picture shows both the normal condition of soil and heavily compacted soil. In the second picture, we can see a lot of tracks in the field that has a detrimental effect of plant growth, excessive moisture. The fourth picture demonstrates unsatisfactory plant growth in the field with heavily compacted soil. What are the ways of addressing this problem in our opinion? Firstly, a properly selected path of machine motion in the field, particularly this concerns tractor turns. Secondly, properly set up agricultural machine which is connected to the tractor. And thirdly, the use of dual tires. In my opinion, this aspect is very important nowadays. In this slide, we have shown the start and end of the tuning path. On the right, there are the formulas for designing the path. In addition, there is a formula for determining the amount of time spent for the tractor tuning. This is quite important when designing the tractor motion during work in the field. This slide shows the main forces which make impact on tractor during the work with the agricultural machine in the field. Formulas for calculation of tractor wheels response to the soil in the field are also presented. Being aware of this response, we can find the tension rising and accordingly change in soil density. This is important particularly when using four-wheel drive machines. In addition, while changing the tractor draw mechanism parameters, we can evenly spread the tractor loading on the soil. This slide shows how the basic parameters of the tractor draw mechanism affect the load distribution on the tractor wheels. This quadrangle shows the area where the parameters of the tractor draw mechanism are properly selected. In these graphs, we can see how soil compaction affects the use of paired mowers. For our experiment, we have used a case 340 Magnum. The experiment has been conducted both with the use of dual propels and standard equipment. This graphs its tractor with standard equipments, and this graph use dual tires. This slide shows a device for determining soil density. We have obtained a patent and tested this device in the field. The cylindrical shaped device is more convenient for its use as it is easy to be placed in the soil, and we more time use cylindrical this device. This table contains the data indicating how the change in the soil density affects yielding capacity. Wheat, oats and rye as one of the main crops are shown as well. This table shows that if the soil density is increased by 0.1, the yield will be decreased by 2 centners per hectare for wheat, 6 centers per hectare for oats, and 12 centers for barley. Thank you for your attention. In this slide, you can see conclusions for my presentation, and wait for your question.
Okay, interesting.
Yeah, we thank the Dr. Solaro to share his study with us. And the next study is named An Approach to Net Classify and Recognize the Sheet Metal Features according to step 10303. The ID number of this study is 90. And we have a video file as well for this study. And I will run this video file now.
Bismillah ar-Rahman ar-Rahim. First of all, I am too much thankful for the organization team in the International Conference on Advanced Material Science and Engineering and High-Tech Devices Applications, and especially Professor Hakan Ates for the great efforts to make this event a wonderful event, and thank again to give me the chance to present my lecture in this great event. My presentation title, An Approach to Optimum Classification and Recognition of the Sheet Metal Features According to Step 10303. Presenter Dr. Hussein Mohammed Abdel Menem, Helwan University, Cairo, Egypt. My agenda for presentation: what is feature recognition, categories in feature types, problem definition, literature review, research gaps, feature recognition algorithm, steps of work, significance of research, and conclusion. What is the feature recognition? The features in computer-aided design CAD software can be called as a region of a part with some interesting geometric or topological patterns. Also, manufacturing features refer to all sorts of information such as shape, functional or manufacturing information. That means that all information of the part or the manufacturing part, including the CAD file features. Recognition of features from solid models is considered as a bridge from CAD to computer-aided process planning, computer-aided manufacturing, computer-aided inspection planning, computer-aided picture planning, computer-aided picture designs. Also considered as the key to the integration in the model manufacturing. There is many categories in feature types. There is categories in prismatic features. This mainly work with milling machines and drilling machines. Also categories for rotating features that's mainly working for turning machines, and categories of sheet metal features, as this mainly work with stampings operations, and also categories of reform features, and also can be work as a shell of the aerospace structures like cars or planes. Here's the problem definitions. Automatically feature recognition from the geometrical CAD data of the manufacturing part is insufficiently applied in real industry yet. There is no complete research work can cover all the features included in the manufacturing part. Many researchers on automatic feature recognition field have proposed algorithms to recognize the combined and interacting machining or stamping features, but these algorithms are not often compatible with all CAD systems. Not general algorithm to include all the machined or stamping features. In sheet metal products, there's many products made from sheet metal like cars, food industry, like cans, electrical panels, home appliances, refrigerators and washers and machines. Different kind of products can be made from sheet metal. Uh, to classify the sheet metal features, mainly the sheet metal features work between two-dimension sheet metal features and three-dimension sheet metal features. Two-dimension sheet metal features like piercing, planking, notching. Also the three-dimension features like bending, deep drawing, forming, and hemming. This sample for the feature in case of two-dimension or three-dimension features. The relation between the process planning feature and the process types. If we find a hole, that means we have a process or process type like piercing or planking process. If we have a bend in the sheet metal feature, that means that we have a bending process or made by bending process. If we have a two-dimension feature and also two-dimension feature like a washer, that means we have a compound process. If we have a two-dimension feature together with the three-dimension feature that we have, it means that we have combination process. If we have more than two features, this means we have a progressive process. If we have higher number of features and steps, this means we have a transfer process. As a CAD file format can be divided into a standard or non-standard. Standard like step file, STL file, or DXF file. Step file mainly work in three dimension only, and the STL file like works also in three dimension only. There is many others like IGES also and GT. Also DXF file work in two dimension and three dimension. This called as a standard files or standard CAD files. The non-standard CAD files like DWG in AutoCAD, in case of AutoCAD, and this we can find this DWG for two dimension and three dimension. And we have a solid part or solid part. This extension of main extension of the SolidWorks, and this work only with three dimension. If we look to the standard CAD file format, as example for DXF working with for two dimension, we can find it is written in a readable language. Also for step 3D, also read in a readable language. We can recognize words like circles, lines or vectors, whatever. And also for STL file, we can find a readable format or readable text. We can read and we can extract data from these files. But if we will look to non-standard CAD files format, such like DWG or SolidWorks, it is not readable and we can't recognize any data from these files. As a literature review, there is many researchers work in the field of sheet metal features. We will discuss work for three of them. As example, Hamouda Musa in 2005. Hamouda made a system. This system to recognize the feature from step file. This part drawn in CATIA and saved as a step file. Use the visualbasic.net to recognize these features. He include about 11 features, features from outside the part, feature from inside the part, and also one feature for bending and one feature for drawing. Suham, he depend only on AutoCAD and Autolisp for AutoCAD. He focus his work to recognize the parsing operations or parsing features or blanking features and bending features and also added drawing features. Yogesh, he in 2015 uh, he worked to simplify the sophisticated shapes of sheet metal parts into a simple shape as a wireframe, and from this wireframe he can recognize easily the part, the feature of the part from this simple shape of the part. He first converts part from a 3D model to wireframe model, and from this wireframe model he can recognize the feature. He developed his work in 2016 to recognize the intermediate features from inside the part itself. Our proposed technique for sheet metal feature recognition, we build a database include about 49 shape of piercing parts, piercing features. These piercing features recognized or selected from the catalog of Musumi catalog. First, the software input as a step file. We convert the part to step file and extracted the data. For each surface or for each piece in the part, as we selected here or recognize 7 faces, in each face we find some features. As example, this 6 bending features, angle 19. In all the part, the sheet metal part, we have the first face or one face has 2 holes. If we have 2 holes, that means that we have 2 piercing operation here, and the process included, and one face has 1 slot and 2 hole. That means that we have 3 piercing operation, 1 for the slot and 2 for the holes, and 1 face and 2 slots and 1 hole the same. That means here from the first column here we recognize the features included in the sheet metal part, and according to this we can recognize the process related to these features. We have an algorithm to recognize these faces and the features included in these faces. The algorithm reads the step file and detects the features, all the information included in these features, especially topology and geometrical types, number of connectivities of edges in the face. Starting from the start, he reads the step file and getting the faces, and after that getting the features including in each face according to this flow chart. In fact, we have in our proposed system 49 piercing operation selected or getting from the Japanese catalog for company called Misumi. We try to make a classification for this according to these features. According to this, we make related to this piercing operation, we make the shallow drawing operation according to this piercing operation, and try to generalize these features according to the piercing features of Misumi. Of course, not all the features can be included. The same feature, the shallow drawing, not equalized for the same feature of the piercing. Also, we have a parsing operation according to this bunching operation from Sumi also, and it can be part of the shallow drawing and part from the bunching operation. According to these features, we can work with the same features according to this. This is considered as the initial for the classification system. As a first step, we work with the features in the two dimension, and we have here a part in this SolidWorks program screen, a part including 3 features. This part have 2 faces, the main 2 faces, the upper face and lower face, and in each face there is a features. From our system, we can get an Excel file as a relation between features and faces. That means that we have in the face 1 as a feature circle, and also for the face 2, the lower face, as the same feature, the circle, and you can recognize this for all the part. Also, as a feature 4, you can recognize another feature. That means the part, the outer dimension part for the part is this rectangle features recognized also for the outer shape for the part. As example number 2, we have here part include 2 holes, circular holes, and 2 slots in different dimensions, and 2 squares, and the outer shape as a big square. So we can recognize these features here as a relation between face and the feature. After we maximize our work to make a relation in 3 dimensions between the feature also and the faces, we can find a relation, and we can define the relation between the face and the feature, and the relation between here as example for feature number 1, as a relation between face and the feature number 1, we have a line, and between also face 0 and feature number 2, also a line. According to this, we can find all the features. We can find all the relation between features in the part, on the sheet metal part. In this case, we can consider this matrix as a fingerprint for the part itself. The same way we can find it for the slot shape for the part, for slot piercing shape of the part. We can also get a fingerprint for this part according to the same methodology, and get a relation between the features and the faces for each part. As example, this is a feature number 1, and this is a face, the outer is a face, and this is feature number 1, and you find that there is a curve. C, it means a curve between the feature number 1 and the face 0. And according to this, you can recognize all the data according to this shape. This data stored in the shape of matrix, and this matrix represent this feature. So if we recognize this matrix, at the same time we can recognize the feature itself. For as all the other features included in our classification, we can do this for the all, and also we can fill the relation in our matrix to include the fingerprint of this feature. Finally, the conclusion of our research work, we defined an easy and simple way to detect a feature from a part model step is presented here in our present work. we are developed algorithm for the feature recognition, and the database developed is presented along with the implementation. Database recognizes feature and their description in a BART model. Feature database is developed in order to make easy process of feature separation and insertion for the development stage and development of process plan. Identified features can be suppressed from the model when it is required, and the suppressed entities, geometry and topology are filled by the extending the adjacent entities, and the part model is rebuilt, which can be used in other application of the product development. Sheet metal with cut out features and the simple deformation features are considered. More complex features such as intersecting features, overlapping features need to be further studied in the future work. Thank you for your kind attention.
Hakan Hocam sesiniz açık değil galiba.
Sorry. Thank you for this good presentation to Dr. Hussein Mohammed. He is really good at to define the materials as three-dimensional. I have been following his studies as well. Now, we are going to continue with the next study, but the next study is effect of thickness on some optical properties of zinc oxide thin films. Dear Asma Zor will present her study, but I think she is not here right now, and she hasn't sent any video file. So we are going to continue with the next presentation. The next presentation is a review about current status and future of blade vein materials. Is Dr. Osman Dur here now? But he sent us a video file, and I will share this video file for you right now.
Ladies and gentlemen, my name is Osman Dur. I am a CEO of the TR Motor, which is developed aero engine companies. Today, I am going to present you a review about current status and future of blade and vein materials study. Now, I'm going to show my outline. This is my outline. I'm going to start with basic definition of blade and vein materials. After that, I'm going to mention about the requirements, limitations, and solutions for blade and vein materials. Then, alloy design will be explained for single crystal materials, and it will be including the optimization of chemistry for single crystal superalloys. After that, the generations will be explained as first, second, third, fourth, fifth, and sixth. Then the newest technology will be explained with CMC materials, which are hot topics for the researchers and aerospace industry because of lightweight and less cooling needs. Lastly, the conclusion was shared as an overall consideration. Blade and vane materials. Blade and blade materials are critical parts for aero engine. The parts of engine provide the flow of the air in the engine fan to nozzle with increasing temperature. Fan, compressor, and turbines includes blade components. Blades can be part of a disc, which is described as blisk. On the other hand, blades put together the discs with a dovetail blade roots. Vanes are fixed in ring formation inside the case for a compressor or turbine. Their purpose is to guide the inflowing air at an optimal angle onto the blade, which are fitted to rotating shafts. Blades and vanes can be found in cold or hot sections. You can see in the figure above, the most challenging section for blades and vane is turbine, which includes high pressure turbines and low pressure turbine components. In this section, blade and vane materials are exposed high temperature, high pressure, and high corrosive environment. Temperature rises up to 1100 centigrade in here. On the other hand, blade materials are rotational parts, rotate with this component at high RPM value. Because of that, circumferential loads are very important for designing of these components. Fatigue and creeps are main concerns. These are the requirements, limitations, and possible solution for blade and vane materials. High strength and high temperature is the most important issue for these parts, and single crystal casting is a solution for high temperature usage with elimination of grain boundaries and their problems. Creeps and fatigue resistance are again related with the removing of grain boundaries. Oxidation and corrosion resistance can be handled by TBC, EBC coating, and ceramic matrix composite usage. Cooling needs is another concern for blade and vane materials. CMC materials do not need high amount cooling. Lightweight again related with the performance and high thrust. Ceramic matrix composites have 3 times lower density than when compared with single crystalline nickel-based superalloys. Alloy design is the first step for development of metallic alloy. You can see an example for alloy design in figure. Single crystal alloy have different phases. However, the most important 2 phases are gamma and gamma prime phases. Gamma phase, the matrix phase. This phase can be observed as a face-centered cubic form and contains solid solution elements, cobalt, chromium, rhenium, and tungsten. The matrix is non-magnetic because of the nickel's third electronic shell. And the property brings about alloying capability of the alloy with alloying elements without phase loss. The alloy elements, assembling mainly the gamma matrix, belong to group 5, 6, and 7 and are cobalt, iron, chromium, molybdenum, and tungsten. Gamma prime phase, the precipitate phase. This phase can be observed as face-centered cubic form and enhance the material overall strength at elevated temperatures, L1-2 ordered structure like nickel aluminum. Gamma prime is quite ductile phase and does impart strength to the matrix without lowering the fracture toughness of the alloy. On the other hand, the other phases can be observed, carbides and borates. For the optimization of chemistry of single crystal superalloys, there are three different ways are used by alloy designers. Gamma prime, gamma volume fraction should be designed very attentively because this ratio gives maximum efficiency at 70%, not 100. Gamma prime used as strengthening phase, however, it should be added charely. Lattice misfit is another concern for optimization of chemistry. Lastly, the creep strengthening elements should be added attentively because these elements can be caused to occur topologically closed packet phase. This phase can be reduced to creep life as a needle form inside the single crystal structures. Requirements of aero engine are being increased day by day. For example, some aero engines should be available for supercruise mission conditions which need higher temperature creep resistance materials. Engine performance is directly related with lightweight, better combustion, and high temperature. Single crystal nickel-based superalloys developed for meeting these challenging requirements with elimination of grain boundaries. Element addition microstructure orientations and heat treatments are used for reaching the desired properties. Lastly, the generation are varying according to the elements they contain. As you see in the figure, oxidation resistance of single crystal was increased with different generations. Also, the strength creep and the other properties was increased. First generation single crystal nickel-based superalloy was derived from directionally solidified materials for increasing creep life. The most important improvement was removing of grain boundaries. When compared with directionally solidified alloys, molybdenum, titanium, and tungsten contents are increased for reducing of bulk diffusion rate that also slow down the corrosion kinetics of the gamma precipitate. These molybdenum and titanium addition increase the solid solution hardening effect with large atomic radius. Controlling of this diffusion controlled mechanism was successfully done. Optimization of gamma prime, gamma ratio again successfully completed in this generation. As you see in the picture, these are the elemental analysis and densities of the single crystal. On the other picture, PVA 1480 vein pairs are shared which were used in F100 engine. In the second generation, alloy designer added the rhenium for increasing creep performance. This addition gives approximately 30 degrees Celsius advantage. Rhenium also increased the solid solution strengthening capability with small clusters which are obstacle for dislocations. Cobalt content was increased 5% to 10%. Chrome content was decreased 8% to 5%, to decreasing of butyl TCP phases proportion. Hot isostatic press was used first time for disappearing of authentic phases, carbide porosities. And incipient melting, you can see in figure 10 the hot isostatic press example. This application was part of production, the famous second generation CMS-X4. The importance of crystal growth direction was understood in second generation alloy. In literature, 001, 111 and 011 direction crystal growth were compared. As you see in figure 9, PVA 1484 is better for life and creep than PVA 1480. PVA 1484 is second generation alloys. In third generation, rhenium addition was increased from 3% to 6% for better creep performance. chromium was decreased to 3% for preventing high proportion of TCP phases. Cobalt level was limited at 3%. Maximum use of temperature of third generation S6 alloy are approximately 40 centigrade higher than second generations. High rhenium ratio was triggered unstable phases. Secondary reaction zone was observed. This was the main reason for formation of cellular colonies. Moreover, this was main reason of life reduction. As you see in figure, CMS-X10 is better than second generation alloys for strength. TMS-75 is another third generation alloys which has better Larson-Miller parameters than second generation CMS-X4. Ruthenium was used first time in this generation in order to decrease grain boundaries TCP and CRZ. Ruthenium was used as a phase formative, which is stronger than gamma phase. For preventing from TCP, chromium was decreased. Cobalt ratio was increased. As you see in figure TMS 138, fourth generation superalloy is better than the other generations than when compared with fatigue and crack performance. Also, PVA 1497 was better than PVA 1480 for crack properties. This generation was developed for refining gamma over gamma prime MOSFET. The rhenium content was increased for CREP and thermomechanical fatigues. Ruthenium content was increased for microstructure stability. This increasing was changed the possibility of addition platinum group metals. The lattice MOSFET has been increased toward higher negative and result in the formation of fine gamma over gamma prime interfacial dislocation network that attributes to a great degree of strengthening. Decreasing of chromium level was the main reason of decreasing of oxidation corrosion resistance. In the generation, the most important loss was corrosion oxidation resistance. As you see in the fatigue, TMS 162 is much more better than old generation. However, TMS 196 mass change very high when compared to others. For eliminating of corrosion bad feature, a sixth generation was developed. Today, sixth generation alternative material studies are continuing. Fifth generation contains high rhenium, ruthenium, and molybdenum. These elements block the aluminum oxide formation at the surface and decrease the corrosion oxidation performance. Cobalt, tantalum, and aluminum content were increased for corrosion and oxidation resistance. As you see in the figure TMS 238, sixth generation materials better for strength and corrosion properties when compared with the other generations. Ceramic matrices composites are the newest technology in the sector for hot section blade vane application. These materials densities 3 times lower than nickel-based superalloy, approximately 2 and 2.5 gram per centimeter cube. These materials are better for toughnesses than ceramics. Because of the CMC materials' own properties, less cooling is enough. Also, this can be main reason of the increasing turbine inlet temperature. Turbine inlet temperature increasing directly support the performance of aero engine. In these materials, environmental barrier coating material coating is used, which is advanced ceramic system and used for different purpose. CMC materials gives 250 degrees Celsius advantage when compared with single crystals. However, it has low toughness. Because of that, stationary parts are more available for CMC usage. As you see in figure CMC materials, specific strength is lower than the metals. Another picture shows the temperature capacity of the CMC materials, which is very higher than metallic alloys. As a result, for meeting the high temperature and lightweight requirement, nickel-based ASICs, superalloys, and CMC materials can be used. Nickel-based ASIC superalloy can be investigated in different generations groups. Every generation is developed with different concerns, and last generation ASICs alloys are better than the first generations about fatigue, scraps, strength, oxidation, and resistance characteristics. CMC's low weight and less cooling need properties are very important for aero engine. CMC materials may be used as billet and vane materials. However, structural parts are more favorable. Designers should choose the materials with trade-off analysis. Now, this is the references. Thank you very much.
Now, we finished all the presentations in this session, except one. One presenter hasn't come yet, dear Asma Zayer. I'm gonna wait for a while. Maybe she comes here. And that's why I will take a short break. After that, I will end the session. Oh yes. As we complete all the presentations in this session, the presentations were very successful, in my opinion. I would like to thank all the participants, listeners, supporters, and organizers on behalf of the organizing committee. I would like to thank especially Dr. Hakan Ateş for his intense efforts. On to your contributions, I think this symposium is keep going successful and good. Now I am finishing the Sunday morning session of the conference. Thank you.